Hello and welcome back, and today we will understand a very interesting idea in fluid motion, that is Bernoulli's equation. Simply put, it says that when a fluid flows through a pipe or along a streamline, speed and pressure are linked. If the fluid speeds up, its pressure drops. If the fluid slows down, its pressure rises. And this relationship holds true as long as the height stays the same. So let us dive deeper into Bernoulli's equation because it covers the aspect of height of flow as well. So when I first learned Bernoulli's principle, my instinct was that higher speed at a point should mean higher pressure. And I'm sure many of you have thought the same. But if you think carefully, that can't be right. If the pressure at this point were greater than the pressure just upstream, the resulting pressure difference would actually push back against the flow and slow it down. But what we observe is the opposite. The fluid speeds up from point 1 to point 2. That means the pressure at point 2 must be lower than at point 1. So it was Bernoulli who expressed this idea in a very elegant way in his famous Bernoulli's equation. Now, over the years, I've realized that the best way to understand Bernoulli's equation, or for that matter, any other equation or formula, is to derive it, because that also eventually helps you work around complicated physics problems. Now, Bernoulli's equation works only under certain conditions. One, the fluid must be steady, that is, the flow should be steady. So it follows clear streamlines without sudden changes. 2, the fluid should have very little viscosity, meaning we ignore friction losses. And finally 3, the density must remain constant. In other words, the fluid should be incompressible. And these are the assumptions that make Bernoulli's principle valid. So imagine a fluid flowing through a tube whose cross-section and height can change, measured relative to some reference level. Let's focus on one section of this tube and study the volume of fluid contained in it. Now, Bernoulli's equation is all about how the energy of a fluid changes as it flows. So, to understand that, we'll use a key idea in physics. Imagine you're pushing a box. If you push it forward and a friend pushes back, the box only speeds up if your push is stronger. So the change in its speed depends on the net effect of all the pushes and pulls. This exact idea is called the work energy theorem. It states that the net work done on a fluid, that is the sum of all positive and negative work, is what causes the change in its kinetic energy. So our plan is to calculate the work done by the pressure behind the fluid and the work done against the pressure ahead of it, and the work done by gravity. And adding them all up, we will know exactly how much the fluid's kinetic energy changes. So let's consider this carefully. At one instant, this section of a fluid is at this position. And after a short time delta t, it has moved forward. Since the fluid is incompressible, the same volume that moved forward at one end must have come out at the other. Now, notice something important. If we look at this overlap, which is part of the fluid that was present at both times, nothing really changes there. Its speed and height stays the same. So its contribution cancels out when we look at energy differences. The real change comes from the volume of fluid that moved forward during time delta t and the equal volume that has exited this side. So this is where we'll track the change in kinetic energy and the work done by forces. Now let's visualize what's happening. Suppose in a short time delta t, the fluid front on the left moves forward a distance delta L1. That motion pushes the fluid on the right to move forward too, and its front shifts by a distance delta L2 in the same time delta t. And because the fluid is incompressible, the volume that enters on the left must equal the volume that leaves on the right. So the incoming volume is A1 delta L1 and the outgoing volume is A2 delta L2. Since these have to be equal, we write A1 delta L1 is equal to A2 delta L2. Now, if we divide both sides by delta t, the time taken, we get A1 V1 is equal to A2 V2. And this relationship is what we call the continuity equation. It's just the idea that mass cannot suddenly appear or vanish inside the pipe. So for an incompressible fluid of constant density rho, the mass flow rate at one section rho A1 V1 must equal the mass flow rate at another section rho A2 V2. So you can say that the volume flow rate or the number of liters of fluid passing a point each second is constant throughout the tube. In simple words, whatever volume goes in, the same volume must come out. Now, for the fluid here to move ahead, you need a certain force to push it. So let us say the required force is F1. And since this force moves this section of water a distance delta L1, it means it has done a certain amount of work on it. And let us label it as W1, which would equal F1 delta L1. Now, if you write the force F1 here as a product of pressure and the cross-sectional area, this equals P1 A1 delta L1. Also note that the work done here is positive because you can see the direction of the force and the displacement is the same. Now, before we go further, many students wonder, where does this pushing force actually come from? Remember, in a moving fluid, we don't have to track the details of the pump or source. What really matters is the pressure exerted by whatever is behind this section. And if you recall the idea of a free body diagram, we only care about the contact forces acting on the boundary of the section. That's what we call F1 here, the force on the fluid coming from the left. Now, at the other end, the work done on this section of the fluid by force F2 will be negative because you can see while the fluid is trying to come out or move in this direction, the force is acting against the direction of displacement. Then work W2 can be given as W2 is equal to minus F2 delta L2, which equals minus P2 A2 delta L2. Again, this pressure P2 depends on what's next to the fluid at this end. If the fluid stays inside a pipe, the pressure comes from whatever fluid is still ahead of it. But if this end of the pipe is open to the air, then P2 is just the atmospheric pressure pushing back. Next, let us not forget about gravity, that is also force and therefore does work on the fluid. Think of it this way, if a chunk of fluid starts out at a lower level and ends up at a higher level, it has to gain height against gravity. So a mass of fluid that was at height h1 is now at height h2, and the work done by gravity is equal to the weight of that fluid multiplied by the change in height, or W3 is equal to minus mg into h2 minus h1. And this work done is negative because you can see that while the displacement is in the upward direction, the force of gravity is acting in the downward direction. So we can say that the total work W done on the fluid is W1 plus W2 plus W3, which is nothing but P1 A1 delta L1 minus P2 A2 delta L2 minus mg times h2 minus h1. Now, according to the work energy theorem, the net work done on a system is equal to the change in its kinetic energy. And here the initial kinetic energy was half mv1 square, and time delta t later, the final kinetic energy became half mv2 square. And therefore, the change in kinetic energy delta ke is half mv2 square minus half mv1 square. Then if we equate the change in kinetic energy with the total work done, what we get is this expression. Now here we know that the mass of fluid moved is m is equal to rho a1 delta L1 which is also equal to rho A2 delta L2. So if we put these two expressions over here in this equation, what we get is this. Now using A1 delta L1 is equal to A2 delta L2 from continuity equation, this becomes half rho A1 delta L1 V2 square minus half rho A1 delta L1 V1 square equals the right hand side. So this is the expression you get. And you can see A1 delta L1 cancelling off wonderfully to reduce this to half rho V2 square minus half rho V1 square is equal to P1 minus P2 minus rho G H2 minus H1. And if you rearrange this equation in a way to reflect the situation of the flow at these sections, what we get is P2 plus half rho V2 square plus rho GH2 is equal to P1 plus half rho V1 square plus rho GH1. And this is Bernoulli's equation, showing that along a streamline, the sum of pressure energy, kinetic energy per unit volume, and the potential energy per unit volume remains constant. And since point 1 and 2 can be any 2 points along a tube, Bernoulli's equation can also be written as P plus half rho V square plus rho GH is equal to constant. That is, this expression would be a constant at every point in the fluid, where here h is the height of the center of the tube above the fixed reference level, and rho of course is the density, and v the velocity at this section. Now one question many students ask is, how can pressure be considered a form of energy? The idea is actually quite simple. Earlier we wrote the work done by pressure at section 1 as W1 is equal to F1 delta L1, which is equal to P1 A1 delta L1. And if you rearrange this a bit and write pressure as work divided by volume, you find that pressure is really the amount of work done per unit volume of fluid. In other words, pressure has the same units as energy divided by volume, like joules per cubic meter. So when Bernoulli's equation talks about pressure energy, it basically represents flow work per unit volume. That is, the work done by the pressure of the surrounding fluid to move a volume of fluid into or out of a region. Okay, now you can actually play around with this equation to find some interesting outcomes. So if there is no flow, or V1 is equal to V2 is equal to 0, then this equation reduces to the familiar hydrostatic rule. That is, pressure decreases as you go up. That is, P2 minus P1 is equal to minus rho times G times H2 minus H1. Next, imagine the 2 points we are looking at are at the same height. In this case, the gravitational term cancel out. That means the sum of pressure and kinetic energy per unit volume remains the same between the 2 points. In other words, when the height does not change, if the fluid speeds up, the pressure goes down. And if the fluid slows down, the pressure goes up. So you see, Bernoulli's equation shows us that as fluids flow, pressure, speed, and the height are never independent. They constantly trade energy to keep the balance. And once you spot this balance in action, from water jets to airplane wings, the principle stops being abstract and becomes part of the real world around you.